You have fallen into Event Horizon with John Michael Goddard.
Science is no stranger to the unexpected. While many things are predicted, occasionally something will come out of nowhere that is totally unexpected, and in this case, according to our understanding at the time, should not be. On October 15, 1991, the Fly's Eye detector at the Dugway Proving Ground in Utah detected a cosmic ray that hit the Earth's atmosphere with unprecedented force, 3 times higher than any previously observed particle hitting the atmosphere of the Earth. This particle hit with such force that it was akin to the energy of a baseball thrown directly at your chest. All of this packed into what was probably a single proton, traveling at very nearly the speed of light. Nothing had predicted this particle's energy. In fact, in contrast, it was thought impossible before it was detected. Since then, a number of such particles have been detected at lower energy but still powerful. Most recently, however, the second most powerful cosmic ray, also violating the rules, has been seen. Known as the Ameratasu particle, this new particle, along with the previous particle known as the Oh My God particle, represent some kind of astrophysical process we do not understand, and whatever accelerated them did it at energies exceeding that of a supernova or any other known energetic event in the universe, by far. Moreover, the particles violate a fundamental limit in the universe. Particles with this energy cannot travel intergalactic space without losing energy. The cosmic microwave background itself prevents this, so the source must be relatively close, and as a result should be easily visible given the energies required. It should be obvious. Because of their power, these particles are traceable to the direction in which they came. The Oh My God particle came from an area where there simply is nothing there that could have produced it. Ameratasu is worse. You see, for all its astonishing power, it originated in the direction of the empty wastes of the local void.
We've talked to you before about the benefits of using Blinkist, the perfect way for curious people to learn more. And if you're a viewer of ours, we know you're a curious person. Our producer, Ross, has been using Blinkist to go through and get the key ideas from books by Michio Kaku, starting with his 2008 book, Physics of the Impossible, which is a scientific exploration of the world of phasors, force fields, teleportation, and time travel. The amazing thing about Blinkist is that it allows you to easily access over 6,500 non-fiction books and podcasts. Even if you're busy with life, you can listen to or read Blinks in just 15 minutes and get a good understanding of complex ideas, such as learning how Michael Faraday came up with the concept of force fields, invisible areas or lines of force that envelop a magnet. And with the new Blinkist spaces, you can create a space with friends or family where you can recommend the titles from the Blinkist library in a shared space which your group can access with or without a Blinkist premium subscription. We're incredibly picky about the products we recommend on Event Horizon, and with that in mind, we encourage you to subscribe to Blinkist. Get 25% off Blinkist Annual Premium. Start your 7-day free trial by clicking the link in the description box. Thank you. Joining John today are Doctors John Matthews and Toshihiro Fujii. John Matthews is a research professor at the University of Utah, where he is part of the Cosmic Ray Research Group. He has worked there on a series of experiments studying the origin and nature of the highest energy cosmic rays, particles from space. His most recent project is the Telescope Array, which is an international venture located in central Utah and hosted by the University of Utah Group. Dr. Matthews is also a co-spokesperson for the collaboration. Dr. Toshihiro Fujii is an associate professor at Osaka Metropolitan University. His research interests are to clarify origins and nature of ultra-high energy cosmic rays. He is a member of the Telescope Array Collaboration and Pierre Auger Observatory, which are 2 giant experiments in both hemispheres to observe ultra-high energy cosmic rays. Dr. Fujii is the person who found the Amaterasu particle. He is one of the leaders for the Next Generation Cosmic Ray Observatory.
Doctors John Matthews and Toshihiro Fujii, welcome to the program.
Thank you very much. It's great to be here. Thanks for having us.
Yeah, thanks so much.
Now, gentlemen, you work in a very, very interesting area of science, the study of cosmic rays. So some of these cosmic rays, we know what they are, ejected by supernova and things like that, high energy. But some of these particles come in at impossibly high energies. Now, before we get to that, how do you detect these cosmic rays?
So we detect cosmic rays two different ways. One way is the primary cosmic ray slams into the Earth's atmosphere, and high up in the atmosphere, it blasts apart the nucleus of an oxygen or nitrogen atom or molecule. And then those secondary particles travel a short distance and do the same thing. And before you know it, you have a shower of billions of secondary particles. So some of those secondary particles, indeed many of them, reach the Earth's surface and are spread out over large areas. So we sprinkle the surface of the Earth with plastic detectors with light detection equipment built into them, and you can sample the charge density at various locations. So the primary array of telescope array is 500, more than 500 of these detectors spread across something like 700 square kilometers. And they're each measuring the footprint of that shower when it hits the Earth's surface. The other way we detect cosmic rays is the charged particles as they're passing through the atmosphere. They excite the gases of the atmosphere. And when those gases de-excite, they emit ultraviolet light. So we have telescopes on the perimeter of the surface array, and they look for that track of fluorescence light, nitrogen excitation light, and they observe those tracks. So usually we like to have events that are observed by both the scintillator detectors, the plastic detectors, and the telescopes, but we're able to work with the data from either one or both of them together.
How often does it coincide like that? I mean, how often do you see a particle in both detectors independently?
Well, the scintillator detectors, the surface detectors, they're operational pretty much 100% of the time. They're encased in light-tight dark boxes, and the charged particles pass through those, and then you make your measurement on the density of charged particles. Disadvantage of the telescopes is they're extremely sensitive. They're looking for something that's like a 100-watt ultraviolet light bulb moving at the speed of light. So being so sensitive and so fast, they can only operate about 10% of the time when there's no sun and no moon and the weather's good.
I see. So when you see these particles, the vast majority of them are at energies that are expected, right? And only very rarely do we see one of these ultra high energy ones. Is that a good characterization?
That's a reasonable characterization. We like to go as low as we can in energy because then you can connect to direct measurements like those made on satellites or detectors on the space station. And then we like to work our way up in energy as far as we can go. And the problem is you expect that you shouldn't see anything above about 10 to the 19.6 electron volts because the cosmic rays should collide with the microwave background light, the remnant from the Big Bang, and then they should lose their energy. So if you say something with energies bigger than that, then it must come from someplace pretty close and you should be able to figure out what it is. So if you see things bigger than that and you can't figure out what it came from, then that's a real mystery.
Now, Dr. Fujii, tell us about the Amaterasu particle.
Yeah, so we detected the really energetic particle 2021 May 27 in the early morning in Utah's time, and we really surprised to catch the about 2.4 times 10 to 20 electron volt. So this is the most energetic particle observed by telescope array experiment. So, and I was really surprised to see such energetic particle. But at the beginning to see such energetic event, I thought it was maybe a mistake, but checking the detail of that particle, I realized this is real event, and we are really surprised to detect such energetic particle.
Now, how much more energetic was it compared to a run-of-the-mill cosmic ray originating from supernova?
Yeah, if we compare the supernova acceleration limit of the energy, this is at most 10 to 15 electron volt. So it means at least 5 order of magnitude different compared to the Amaterasu particle. So yeah, it is only possibly accelerated in our galaxy, as you mentioned in the supernova or pulsars, but in our observed event should be an extra galactic origin. This is more and more powerful compared to the supernova.
Now, with the speeds that we're talking about, Dr. Matthews, how fast are these particles moving at that energy?
So if you think of it as a percentage of the speed of light, then it's 99, and you just keep writing nines until you've got like 23 nines out there before you go to other digits. So it's virtually the speed of light, just tiny fraction different than the speed of light.
Now, in regards to the atomic nucleus that made it up, the actual, I know that most of them are protons, but it can be other stuff. Do we have any idea what the material, what element it was the cosmic ray is composed of?
My guess is that it's a proton, but of course we don't have proof of that at the moment. Usually what we do when we want to figure out what the chemical composition is, what element these things are, it's good to have the telescope information because that shows you how the shower developed in the atmosphere. And that's looking at how fast that ramps up, how fast that shower develops. That is what really tells you what the chemical composition is. Another thing you can do, and we're working on, is you can look at just the surface detectors. As Fujii was saying, this occurred in the early morning, so the telescopes were off. So we don't have that data, but there's machine learning techniques you can use to look at all the different variables of the data in the surface detectors, like how many muons there are and the little pulse shapes and what the distribution is of particles coming in during the time you're collecting that event. You can infer from that whether it's heavy or light or maybe a proton, but that data is still being worked on.
Now, the problem with the Amaterasu particle and also the predecessor to it, the Oh My God particle, which was even more energetic, these very high energy particles are on the order of 2 to 3 times more powerful than a normal cosmic ray. The problem is that not only do they not seem to have a ready source, they also come from nowhere when you trace them back. So what goes on there? How can you tell the direction of the particle? Just its trajectory, I guess?
Yeah, so in the case of the Oh My God particle, it was observed by telescopes. So what you're observing is a track coming down through the atmosphere, and you give the timing information for each pixel. So looking at the track, that gives you what we call the shower detector plane. And then the timing information gives you the angle within the shower detector plane. So then you can point that back to where it came from. This Amaterasu particle was observed only by the scintillator detector array. There's one detector every 1.2 kilometers, 3/4 of a mile on a square grid. So in this case, what you're looking at is sort of a curved pancake coming down and hitting the Earth's surface and each of those detectors at a slightly different time. So you take all that timing information and you can point the perpendicular track back to where it came from.
Now, Dr. Fujii, when your team first noticed that this particle was real and that it appeared to come from the local void where there's nothing,
Yeah.
what was the discussion like?
Yeah, so I thought it should be coming from nearby really energetic source because we have so many telescopes in optical, infrared, radio, and so on from ground and also space. There already really long time history to of the astronomical objects, and we have a lot of candidates in the nearby universe. However, the direction of the Amaterasu particle was coming from the local void region. This is there are less candidate of the powerful object. So I firstly to notice that things I was disappointed at the first, but next time I getting more and more excited. We see some new mystery.
Now, how often, based on, I mean, do we have enough of a sampling, in other words, of ultra high energy cosmic rays to predict when we might see them on average? In other words, can we say these happen every so and so amount of time?
Yeah. So currently, telescope experiment with continuous. We have the about 50 years operations, but we detected only one Amaterasu particle above 2 times 10 to 20 electron volt. And however, we are now upgrading to the fourfold detection area. It means that every 4 years we detect the energy equivalent with Amaterasu particle. And the next 10 years we maybe 1, 2, or maybe 3 event. And we check that direction is really same direction with original Amaterasu particle and new another. I would say the Susano or Tsukuyomi particles is also related to the Shinto in Japan. So I hope those energetic particles coming from the single direction, and we should see some source of that direction.
It's going to be interesting to see what that source is because it's hard to imagine, even a supernova accelerating a particle to those energies, and it just doesn't seem to make sense. But that's why it's exciting.
Yeah, supernova, as Fujii-san was saying earlier, can only just because of the amount of energy there, they're only accelerating particles up to about 10 to the 15 or 10 to the 16 eV. So in the scheme of the particles that we look at all the time, they're nowhere near energetic enough. So the high energy ones that we're trying to find sources for are much more energetic than a supernova can do. And the goal of the experiment is to figure out what is the sources of those particles.
Do you have any hypotheses so far? I've heard some talk of cosmic strings and things like that may be able to accelerate it, but we don't even know if those exist. So, what are the hypotheses on the table that you're kicking around?
Well, one hypothesis is something called an active galactic nuclei, which is like a supermassive black hole with stuff swirling around it and being sucked into the black hole, and then big jets of particles shot out the sides, the stuff that didn't quite get sucked in. We've been trying to see if those might be sources, or another hypothesis that might fit into the game of Amaterasu and oh my god particle is maybe there's some dark matter or other particle that we don't know what it is, but it's out there and it's massive and it is traveling around, and then just suddenly it decays, and so it shoots off a particle or a pair of particles that have the energy of the mass of the original particle.
Could you take that so far as to wonder if you were seeing something artificial, artificially created, an alien particle accelerator or something like that? Or is that just taking it too far?
That's a little far for me. But I do think there are so many stars and so many galaxies that it's pretty likely that there's other life out there.
No guarantee it has giant particle accelerators, though.
Exactly. I'm not pushing it that far.
Now, with the detectors, so you're essentially working 24/7. Is there any sort of plan to sort of improve the detectors and maybe cover more area of the sky or something like that? That put them in different countries. Are there plans to expand it?
Well, the telescope array, the original telescope array was about 700 square kilometers, and as Fujii-san indicated, we're in the process of expanding it by a factor of 4, so it'll be about 2,800 square kilometers or close to 3,000 square kilometers. Interestingly, that's about the size of another experiment called the OJ experiment, which Fujii-san's also part of down in Argentina. So, sort of as far south as we are north, and sort of in a similar part of the ecosystem where it's very dry and sort of deserty. So, they're running an experiment down there trying to see the same thing. One interesting thing is in the southern hemisphere, for some reason, they seem to observe a lot fewer of these high energy particles. So if you reduce the energy cut to just 1 times 10 to the 20th and ask how many events telescope array has observed in the first 14 years of data, that's 30 particles above 10 to the 20th EV, which is not very much, and they look like they're scattered all over. So, like Fujii-san was saying, getting a lot more of them would be really helpful. But somehow in the southern hemisphere with a detector that's 4 times bigger and has been operating a little bit longer, they've only seen like 45 or 48 events. So something is definitely curious why the southern hemisphere, which sees the galactic center, is seeing so many fewer really high energy events.
Dr. Fujii, can you tell me more about the detector in Argentina and your work there?
Oh, yes. So the size of the OJ observatory in Argentina is 3,000 square kilometer, and the operation was started from 2004. And and OJ experiment observed the indication of the cosmic ray should be an extragalactic origin based on the anisotropy based on some cosmic ray access to the outer, very far away from our galactic center. And we believe the cosmic ray should be an extragalactic origin. And this is one great achievement of the OJ. So the detector itself used in the water Cherenkov detector. This is the same technique used in the super Kamiokande in Japan. The particle in the medium faster than the light speed, it emitted the so-called Cherenkov radiation. So that signal are detected by the detector, by the surface detector. That detector is different with the telescope array. And but we need to understand the difference of each detector, and we recently actively working about the joint working group between the TA and OJ, and we study our detector, TA detector as OJ detector. This is really difference or not difference. So we are now dedicated to study about it.
Now, Dr. Matthews, give us an overview of what creates the Cherenkov radiation. What is that? Well, I know the answer, admittedly, but tell the audience how that happens.
So, as we said, particles like Amaterasu or even lower energy particles, they travel through either the atmosphere or a water tank. They don't lose any speed. They might lose a little energy, but they're not losing any speed. Meanwhile, when light travels through those media, it slows down by the index of refraction. So if you're in water, the light is slowing down a lot, like 60%. And so now you've got a charged particle that's passing through the medium, and it's going faster than the speed of light in the medium. So not faster than the speed of light, just faster than the speed of light in the medium. So when it does that, it generates a shock wave similar to a sonic boom or a boat traveling on the surface of a lake faster than the wave speed of the water. So that shock wave is light, and that's called Cherenkov light. You can observe that.
And it is also the blue glow that one sees in the water of nuclear reactors, although a little bit different content there.
Yeah, that cool.
And I've always, yeah, it's a beautiful blue glow. I've seen it. And it almost gives you the chills because you know the mechanism that's creating it, but just the idea of something exceeding the speed of light in a medium glowing blue. Now, what can you do further as far as detection of these? So you've got north and south covered. Could you put a detector in Europe and cover an even wider area?
You could, or maybe further north in Chile or something. You'd get better coverage. You do need a reasonably high, dry place. Another idea that we've been working on with various groups is to put detectors either on satellites or on the space station. Then you'd get better coverage over larger areas all at the same time. Has a lot of challenges getting the optics to work because now you're much, much farther from the cosmic ray tracks. So it's a tough measurement to make, and it's likely to be expensive because you're putting it on a satellite or the space station. So you got to build something extremely reliable, and you got to get it up there. So it'll be a lot more expensive than what we're doing now, but certainly very interesting.
Now, what happens? So when this thing hits the atmosphere and dissipates its energy, when one of these particles, a proton traveling at very, very high relativistic speeds, when it hits with the energy essentially of a baseball being thrown, or maybe even a little bit greater than that. A single proton hitting with that kind of energy. What happens when this hits something in space? In other words, the International Space Station, if it got hit with a high energy cosmic ray like this, would it just go right through it, or would it create a problem?
It'll mostly go right through it. It will cause some damage to various components. If, for example, if it hits a computer chip, it'll cause some damage in the computer chip. A small amount of that shower that develops in the atmosphere will develop in the computer chip, or humans, right? There's humans on the space station. They're being exposed to a lot of radiation. So yeah, it'll cause a little bit of damage. Not huge. Mostly the energy won't be all dissipated in the chip or the person or the metal of the space station, but a little bit of the shower will develop, and there will be a little bit of damage.
And it's constant. But cosmic rays in general also are sort of a challenge for space travel anyway, right? I mean, they flip bits and they do all kinds of stuff. What are some of those challenges?
Well, like you said, they flip bits, they damage various electronic components. If you're an astronaut and you're caught out in that all the time, your chromosomes are being changed and your DNA is being affected. If you're stuck on Mars or stuck on the moon, you need some protection. Here on Earth, you not only have the atmosphere to protect you, but you also have the Earth's magnetic field, which sweeps away a huge amount of the cosmic rays and sends them off to the North Pole and the South Pole.
But not these high energy ones, right? They're just too high energy to...
Yep, exactly. The low energy ones are the ones that get swept away to the poles. The high energy ones mostly come straight in. Luckily, if you look at the frequency that cosmic rays arrive, for every factor of 10 you increase the energy, the rate that they come in and hit the Earth at falls by a factor of 1,000. So if you hold out your hand, 1 per second is going through the palm of your hand, or like I like to give students a hard time, 2 per second through your head. But when you get out to the really high energy ones, like the Amaterasu particle, or even a little bit lower, it's 1 per square kilometer per century. So the odds of getting hit by such a thing are pretty small.
Now, Dr. Fujii, in regards to cosmic ray science, is there any advantage to doing it at the poles where they're concentrating?
Yes. So I think in the Earth we have the very nice atmosphere. So this is really suitable to detect the most energetic particle. So, and as Professor Matthews mentioned, some colleagues studied from the orbit in the space to detect such signal from space, but we also try to make a further bigger area from the ground. So currently there are two big collaboration in telescope array collaboration in the northern hemisphere and PLOJ observatory in the southern hemisphere, and the ground coverage gonna be 3,000 square kilometer if TA fourfold expansion was constructed, and we try to think the further next generation observatory in the ground of the Earth, and the total ground coverage gonna be 30,000 square kilometer. So we try to spread all over the world with such huge detector like telescope array and the PLOJ experiment, and we try to catch the one order of bigger magnitude array from the ground. So I think the Earth is a very nice place to build our cosmic ray detector, and we hope we would like to challenge to find the origin of the energetic particle.
Now, what of studying cosmic rays directly in space? How do we do that, Dr. Matthews?
So it's mostly like the telescopes that we're currently using at the telescope array and the Auger experiment. The telescope array, the pixels view like 1 degree of sky, which is huge compared to what normal astronomy telescopes look at. They want to know, very precisely what they're looking at. But we're looking from maybe 30, 40 kilometers away, so that's enough resolution for us here on the surface of the Earth. Now, if you go up to a satellite or the space station, now you're something like 400 kilometers up above the Earth, and you're trying to look at the same cosmic ray shower down below you from a distance of 400 kilometers. So now you need a camera that has a huge field of view, and you need really, really tiny pixels. So you need millions of pixels on a huge camera to try to reconstruct things. Imagine, your camera is okay when you're taking pictures of birds or your friends in the living room or whatever. But if the bird moves 400 kilometers away and you want to take the same picture, that's the improvement you got to make in your camera.
Are there any plans for building such a space telescope?
Oh, yeah. There are definitely people working on it. I work with a group called USO and Poema, and most basically those are mostly European and Japanese, and then an American version, which would be on a satellite. So people are definitely working on this. We launched 3 test balloons, so balloons with test telescopes on them. Unfortunately, launching big pieces of equipment on balloons is a risky business, and both of our balloons that were launched from New Zealand fell down and were lost in the ocean. We do have a test camera, which has a very small field of view, but does have the high resolution pixels, that's currently up on the space station and takes data like in small few hours or a day time period here every week or couple weeks. So they're learning how to do these things, but it's a long, slow process to prove you can do it and observe showers, and then to scale that up to a huge camera, and then to get the funding to do that.
All right, gentlemen, thank you for joining us today. And I look forward to further developments in this because, we're going to see more of these particles. And if they keep continuing to come from nowhere, that's going to be very strange indeed.
Yeah, I'm hoping that we can collect a bunch more data and figure out where these things come from. And if we don't, then we've got another mystery.
Yeah, I agree. And we found another mystery, and let's try to challenge such, to find the source of the most energetic particle.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.